class. Okay, so we're going to look at what we call an RC circuit. So, drew it here. We have a battery, a switch, a resistor, and a capacitor. And so a switch can go, from A or B, terminal A or B. And let's say we flip the switch to position A. And we want to analyze this circuit. And again, we're going to do it in two ways, starting with conservation of energy, which is a good way to look at it because conservation of energy is it's one of the most fundamental rules. We're very safe doing it this way. And so let's consider a time interval dt, where a certain charge dq is going to go through any part of the circuit. We have a current flowing through the circuit just in time dt. Let's see where to write this. The amount dq, which is equal to current times the time interval dt. And so, where the battery has chemical energy that it is being depleted, it's giving that energy to the circuit. And by conservation of energy, whatever the battery is supplying, that has to go somewhere. And so part of it is being converted to heat in the resistor. But figure, this current is, say, flowing in this circuit. That is bringing positive charge to this plate of the capacitor. And of course, the other plate builds up a negative charge. And so there is an electric field in between the plates of the capacitor, and electric fields store energy. So the energy that is being supplied to the battery is going to heat in the resistor and the potential energy of the capacitor. So let's look at this time interval dt. And say a charge dq is flowing in that time. What's being supplied by the battery is epsilon dq. If you have a charge flowing through the battery, it gains this amount of energy. That's basically this equation. Delta V is a potential, or the EMF is just the potential difference, delta V. And so this has to equal the energy being converted into heat in the resistor. So for a resistor, the rate that energy is being converted into heat is equal to I squared R. So the multiply by dt, that gives you the change in energy of the resistor. And for the capacitor, that's going to gain an amount of energy du, where U is Q squared over Tc. So if we take du dq, let's do this here. We bring the 2 down, that cancels out the 2 on the bottom. So that's just Q over C. All right, so let's plug that in. Now let's convert dq to I dt. So that's equal to I squared R dt plus du. So if we solve this for du, that's for the capacitor, that would be Q over C dq. And again, let's write dq as I dt And so if we divide by dt, and simplify this a little bit, you're mixing up, you can use either lowercase or uppercase I for the current. So I tend to mix them up sometimes. So just stick with one and get used to it. But anyways, we have, yeah, I think let's just divide by dt for now. So we have epsilon I equals I squared R plus Q over C times I. So, yeah, we can also divide by I. Just because I'm kind of running out of room. And this is kind of about as far as we can go. Except notice we have two variables, I and Q, that are related to each other. So we can replace I with dq dt. And so we get this differential equation. So again, this is using conservation of energy. And let me write this somewhere. I'm going to write up here and put a box around it. Okay, so this is the differential equation we got using conservation of energy. Now, another approach, admittedly it's an easier approach to do this, is just using the loop rule. So if we say start here and just follow this loop, remember the switch has been flipped to position A. So if we follow this loop around here, first we go through the battery, and then there's a voltage drop across the resistor, and also a voltage drop across the capacitor. Remember, electric fields go from high potential to low potential. So let me exaggerate this capacitor a little bit. So yeah, the electric field, we know this plate, the current is bringing positive charge to the upper plate, which is attracting negative charge to the lower plate. So the electric field is, that red. It's going from positive to negative, high potential to low potential. So there's a potential drop across the capacitor, where that would just be Q over C. Or 1 over C times Q, and then we're back. We've completed our loop, and so the sum is equal to 0. And so basically we have the same equation here. We can move these two terms to the other side, and we can write I as dq dt. Again, we get the same thing. So again, much easier to use this loop rule, but I kind of prefer the conservation of energy approach. Gets you the same place. It's a little bit more reliable though. Okay, so now what we want to do is solve this equation. So let's, this is a separable equation. Let's see, we want to, let's multiply everything by C to start with. I want to just rewrite some things. So we have RC times dq dt plus Q equals C epsilon. So I multiplied everything by c. So we have c epsilon. Here's RC times dq dt. And then just q. And let's do this. So let's write, we'll subtract q from both sides. And now we can get it in a nice form. Let's see. We have room here. So we're just going to move some things around. Okay, so yeah, we basically divide by c epsilon minus q, and then multiply by dt. And now we can integrate this. Let's integrate both sides. So let's start from 0 to some. Here, I'm going to rewrite. This RC is a constant. I'm going to put primes on the integration variables. And just because we don't want the variable to be the same as the variable in the limits to be the same as the integration variables. But at t equals 0, q is a charge on the capacitor. So at t equals 0, q is 0, and then at t equals t, we just have some random charge q. So we want to do this integral. The one on the right is trivial. That's just t. Now on the left, let's make a substitution. Let's let u equals c epsilon minus q. Then du is minus dq. So let's plug this in. I'm going to divide both sides by RC. So we just have the integral on the left. So dq, this is minus du, divided by u. Okay, I guess we should have primes here. And that would then equal t over RC. Now, for the limits of integration, here we had q equals 0. So if q equals 0, u is going to be c epsilon. And then we just had q as some arbitrary value q. So here, let's call this u1 and u2. Actually, I don't want to do that yet. No, yeah, let's do that. Okay, so again, u1, that's when q is 0. So u1 is c epsilon. And u2 would be c epsilon minus q. And now what we're going to do, because we have this minus sign here, yeah, let's move that to the other side. So this integral is now trivial. Du over u, that's a natural logarithm of u, evaluated between u1 and u2. And we have that minus sign in front. So I move that to the other side. I'm going to do something here. This quantity RC, let's give that a name. We call that RC. That's letter tau for now. Let's just call it that. We'll talk about what that is later. Now, the natural log of u evaluated between, we have the natural log of u2 minus the natural log of u1, but because of this property of logarithms, we can say natural log of u2 divided by u1. And now I'm officially out of room. So let's, we're going to clean this up a little bit, but let's make some room. I'm going to write down our result that we got to here. Okay. Now, let's get rid of this natural logarithm. So, just from how they're defined, e to the minus t over tau is just equal to this fraction. And let's solve this for q. Let's here we have c epsilon minus q equals c epsilon e to the minus t over tau, or q would be c epsilon times 1 minus e to the minus t over tau. And this is our kind of final result. We should look at that before moving on, though. So first off, Q is the charge on the capacitor. And so at t equals 0, there should not be any charge on the capacitor. So let's check. Let's plug t equals 0. We have c epsilon times 1 minus e to the 0. So yeah, we do get 0. Now, if we look at a long time period, if t is very large, e to the minus t over tau, that's 1 over t to the tau. So if t is large, we have 1 over e to some positive exponent that's large. Basically, this term's going to go to 0. So the limit that t approaches infinity is just c epsilon. So if we were to plot the charge as a function of time, we start at 0 and we approach this limit c epsilon. And again, q equals cv. So once we're at, once q is equal to c epsilon, let's just plug that in. We'll have c epsilon would equal c times v, which is the potential difference across the plates of the capacitor. We can see once we reach this limit, the potential across the capacitor is equal to the EMF of the battery, and so it's going to stop there. So this current is going to build up and approach this limit. Eventually, it's going to reach that limit. Mathematically, it will never reach that because you have to take the limit as t goes to infinity. But for practical purposes, after a fair amount of time, that's going to happen. Let's talk about time for a moment. We just labeled that this quantity RC was showing up. So let's just call that tau. Let's give it a name. Let's look at the units for RC. Now the units should be seconds. How do we know that? It has to be seconds, or it has to at least be time for the unit, because tau shows up where we have e to the minus t over tau. And if t was not a second, then we would have e raised to the power of some unit, which just doesn't make any sense. You really can't have functions of things that have units like this. Well, you can have some, but certainly not something like this. So if you ever like raise e to something like, say, e to the 1 meter, you might want to think about what you're doing. That's a problem. And yeah, I guess you haven't gotten there in math yet. If you have gotten there, just think of the Taylor series expansion of e to the x. You have like e to the x, 1 plus x, and so on. You know, if you plug in, say, 1 meter, or let's say tau was just a number, it was dimensionless. If we plug in a second, we'd have 1 plus a second squared, and you can't even add those things. Every term would have a different unit. It just wouldn't make any sense at all. So tau better have units of seconds, or time in general. So let's see if we can do that. We have an ohm times a farad. I'm going to erase this. We're going to move some things around. Let's write down Q. So we have C epsilon. We could call that Q max, because that's the maximum charge we can put on the capacitor. Remember, like the battery is pushing charges. Think of the current as carrying positive charge to the capacitor. And this point is already positively charged, so you're trying to force more positive charge, but the charge you're placing is being repelled by the positively charged plate. And so, the more charged that capacitor becomes, the harder it is to put additional charge on it. And once you reach this value, the battery is done. It can't force any more charge because the potential across the capacitor is equal to the EMF of the battery, so it stops. Okay, so we have Q. Now let's focus on this tau. I guess I could leave that up for now. No. So we have current as a function of time. So it's going to look like that. Now, yeah, we're going to look at tau, just the units. So we have RC, that is an ohm times a farad, which better equal a second. Now, we're going to have to throw some unit conversion factors in here. Yeah, let's start over here. Well, the only thing I know of with an ohm is like Ohm's law. So a volt is an amp times an ohm. So we're going to have to use that one. Remember, Q equals CV. A coulomb is a farad times a volt. Oh, this might be easier than I thought. And an amp is a coulomb per second. Current, so amp is a coulomb per second. So an amp times a second is a coulomb. So let's just check it out. So those cancel, farads cancel, volts, coulombs, amps, everything cancels except for seconds. So yeah, tau is measured in seconds, and it is called the time constant. So very important in RC circuits, we have this time constant. Now, let's look at current in the circuit. So I'm going to work it out here, and then we'll write the current. We'll write the result up here. So current is dq dt. So if we take the derivative, the first term, C epsilon, that's a constant. So we have the derivative, which we're going to have minus C epsilon times the derivative of e to the minus t over tau. So the derivative of e to the x is, of course, e to the x, but we have to apply the chain rule. And so that's going to give us, we're taking the derivative of minus t over tau with respect to t. So that gives it, so the minus signs cancel out. So we have C epsilon over tau e to the minus t over tau. Now, let's call this Imax. So, we just have Imax e to the minus t over tau. So that is the current as a function of time. So let me just double check. We have C epsilon, which is, the units of C epsilon are coulombs. So we have farad times a volt, which is a coulomb. And so a coulomb over a second is the right units for current. So I'm going to write down this result, though. The maximum current is C epsilon over tau. Now, let's plot current as a function of time. So we have Imax here. So let's say we flip the switch at t equals 0. According to these equations, as soon as we flip the switch, the current jumps up to Imax. So it just jumps instantaneously, which should cause a little bit of concern. But then as time increases, the current decreases. And again, that's what we kind of talked about earlier. This current is delivering charge to the capacitor. And once you build up charge on this plate, it becomes harder and harder to put more charge. So the current should decrease until we reach basically the potential. The capacitor approaches the EMF of the battery, the current shuts down. And now this jumping from 0 to Imax instantaneously, that is physically impossible. So mathematically, that's what we're getting. Basically, the equation that I erased that describes this circuit, there's something missing from it. Now, that something that's missing is not something important for a circuit like this. There's something called inductance, which we're going to talk about later, that prevents these infinitely fast current changes. And physically, we're talking about actual charges moving around, and so they have inertia. So just based on mechanics, we also couldn't have this current just instantly changing like that. But in a circuit like this, the inductance is so small. If you were to plot the current, if you were to actually graph this, you'd basically see it jump instantaneously. If you hooked up an amp meter, there's an ammeter, it's a device that measures current. As soon as you flip the switch, you'd see the current at its maximum value. It would happen so fast, you're not going to actually see it slowly rise. It's just going to jump. But, there has to be at least some delay. So, that's what happens when we flip the switch towards A. So, I think we covered that pretty well. Now, this time constant, it always shows up along, in this e to the minus t over tau. And a very important, let's say we look at one time constant. Let's look at Q after one time constant. Let's call this Qmax. And I'll write that down here. That was C epsilon. So we'll have Qmax times 1 minus e to the negative 1. So e is like 2.7, so 1 over that, 1 over 2.7, that's going to be like point, here, let's just do this, e to the negative 1. .37 roughly. So 1 minus 0.37, this would be 0.63, we'll say. So after one time constant, you know, t equals 0. Let's start there. So yeah, e to the 0 is 1. So yeah, Q0 is 0. So after one time constant, we're 63% of the way to our maximum current. So like this curve starts out rising very quickly. And let's look at two time constants. So it's kind of the same thing. We're going to have Qm times 1 minus e to the negative 2. You know, we have 2 tau over tau. So e to the negative 2 is 0.135. So this would be, let's see, that would be 865 of, you know, a maximum charge on the capacitor. So it's slowing down. One time constant brings us to 63%. The second time constant brings us to about 87%. And after 3 time constants, let's do e to the minus 3. That's 0.05. So this is going to bring us about 95% of the way. So after 3 time constants, you're 95% of the way to your maximum charge. So again, typically after 3 time constants, you can just say, yeah, you're there. That's like a good rough estimate of how long it's going to take to get to your, you know, to where the current stops and the capacitor is fully charged. You know, 3 time constants is 95%. If you go to 4, let's just do 4. That would take us to about 98%. So, and again, the increments get smaller and smaller. You know, you go from 0 to 63 to 87 to 95 to like 98. And, but yeah, I mean, we're effectively there after like 3 time constants. Okay, so this is called charging the capacitor. So this applies, so like initially the capacitor was uncharged, and we flipped the switch to position A, and we charged up the capacitor. And so let's say now, what if we flip the switch to B? So if we move the switch to B, now the battery is out of the picture. Our loop just consists of a capacitor and a resistor. And this plate is positively charged, this plate's negatively charged, so the positive charge is going to, you know, move around towards a negative charge until the capacitor is back to being, you know, completely discharged. Because, like say there's 1 coulomb here, negative 1 coulomb there. If you take like that coulomb off, this will be neutral. move that coulomb to the negative plate, that's neutral, and then nothing further is going to happen. So again, we flip the switch to B, we should expect a current to go around counterclockwise now, and the current should die off until, it should die off again. And the charge should start at its maximum value. So like here, when you're charging it, you plug in t equals 0, you get a charge of 0 on the capacitor. Here we should start at maximum charge and then drop off to 0. So let's use the loop rule for this, or we could use conservation of energy. You can pick one. Let's do conservation of energy. Let's just consider a charge going around this loop. In this case, the current's going this way, and just to make life easier, I'm going to follow going around, so we consider charge dq going counterclockwise. And so across the capacitor, so moving a charge across the capacitor, we're going from a low potential to a high potential. So that would be like a gain of energy. So in a time delta t, or time dt, we're moving an amount of charge dq. If we go across the capacitor, that charge is gaining energy. And so the amount of energy it gains, let's call that du again, which is, I erased it. Let's write that here. For the capacitor du would be just Q over C. And so we have 2Q over 2C, and 2's cancel off. Okay. So and then that charge, or the charge moving through the resistor, we're going to convert that into, so here for the capacitor, we have Q over C. For the resistor, we're dissipating that energy. And so du for the resistor, that's going to be minus I squared R dt. And if we add these up, we have to get 0 because energy is conserved. So du over all for the circuit has to be 0. So we have minus I squared R. I'm going to try and, we don't need this anymore. So we have minus I squared R dt plus Q over C equals 0. I think I'm missing something. Let me just check. It wasn't clear. Let's go back to this. Sorry, let me. The units weren't making sense. So let's see. If we take du dq, that would be Q over C. So du is Q over C dq for the capacitor. So the units were not making sense, just Q over C, because it should be, charge squared, a coulomb squared over a farad is equal to a joule. So, let's fix this now. Okay. We can also take in a time derivative, and then, but we can just plug in dq as I dt. So let's do that. let's say I squared R dt equals Q over C I dt. And we can cancel out a few things here. We can cancel out an I dt. So yeah, I dt, so we're left with IR here. And that's equal to Q over C. Let's multiply by C. We have RC times I equals Q, or RC is the time constant tau. So, and let's replace I with dq dt. So our final result, we have tau times dq dt equals Q. So that's our differential equation. So I'm going to, let's put a box around this. I'm going to actually move it, but that's what we get. And of course we have initial conditions. Let's write that down as well. Q0 is equal to Q max, which is C epsilon. And we're going to need that. So let's kind of let's write down our basic equation. So this is our equation. That's our initial condition. It's a first order equation. We only need one initial condition. And now let's make some room. And again, this one will be a little easier to solve than the last one. So let's just rewrite this. We can say dq over q equals dt over tau. And now let's integrate both sides. So I'm going to change this to like dq prime over q prime equals the integral of dt prime over tau. So again, let's integrate from 0 to some later time t. And so at t equals 0, we're at q max. And then at some later time, we just have a charge q. So q is a charge on the capacitor at time t. And this is a simple integral to do. On the left side, we have the natural log of q prime from q max to q, and that's equal to t over tau. So the integral of dt is just t, or t prime evaluated from 0 to t, so it's just t. And again, it's dimensionless. T over tau is just a number, which is good, because we're taking a natural logarithm. That should only give us a number. So again, the natural log here, we're going to have natural log of q minus a natural log of qm, which we can simplify. So here we have q over qm is e to the t over tau, and now something has gone wrong. It's going to be minus t over tau, otherwise the charge is just going to keep building up. We're going to start at q equals qm and then just build up from there when the charge should actually be decreasing. So let me think about what happened here. I think it goes all the way back to the beginning. It's probably not careful with the signs for the actual differential equation to start this whole process. There should be a minus sign in there somewhere. I don't think there was a mistake in this part. So yeah, let's go back to the actual differential equation. Yeah, they should have both been positive terms. It should have been this. So I think I missed one of those terms. So this is an easy thing to reproduce, just solving the differential equation, once we get it right. So again, the energy in the capacitor, let's look at that. du for the capacitor. That's where I screwed up. The electric field is getting weaker as the charge is moving away. As the charge is dissipating, the electric field gets weaker. So this term should have also been negative. And so that should be minus Q over C dQ. And then du for the resistor. That's being converted into heat. So, that's that I squared R dt. And so basically, if we just follow what we had before, I'll just do that real quickly. Sorry about this. It's always good to make a mistake right in the beginning. If we add that up, we have to get 0. So we have I squared R dt is equal to minus Q over C dQ. I'm going to write I dt. And so if we multiply by -1 and then divide by I dt, we get IR plus Q over C equals 0. And yeah, that's basically this. You multiply by C, then you have RC times I, so RC is tau times I is dQ dt, and then plus Q equals 0. So yeah, I made a mistake right at the very beginning, so I had to redo everything. But yeah, the electric field stores energy, so as a charge is moving away, that's taking energy. The energy stored in the electric field is decreasing. And the resistor is dissipating energy, so both of these terms should have been negative. So sorry about that. But now, this is a very easy equation to solve. Let's say dq over dt, we'll just start like this, equals minus q. And then if we multiply by dt, and now let's divide by Qn by tau. So that'll give us, dividing by Q and tau, tau cancels out. We have dQ over Q equals minus dt over tau. And then we integrate. So dQ prime, this is kind of where we were before. From Q max to Q. So here's where we were before, except now we have that minus sign, which we need. And so I'm going to do a shorthand here. This would be natural log. Again, we know it's natural log of Q prime. Evaluate these two. So natural log of Q prime, natural log of Q minus natural log of Qm. Or natural log of Q over Qm equals minus T over tau. So that means Q over Qm is e to the minus T over tau. And I'm going to write the result up here. So Q is equal to Qm e to the minus t over tau. And this is for discharging the capacitor. So these equations apply when you're when you flip the switch to A, the capacitor is initially uncharged. You flip the switch to A, that'll charge the capacitor. Once it's fully charged, if you flip the switch to B, the charge is described by this function. And let's plot that. So at t equals 0, e to the 0 is 1. So we start out at our maximum charge, which makes sense because, we fully charge a capacitor before discharging it. And then it decays exponentially. So that same e to the minus t over tau, it's going to give us this exponential drop. And let's look at the current, which we get by taking the derivative. So we have Qm e to the now taking the derivative of e to the minus t over tau is e to the minus t over tau times minus 1 over tau. Now we can simplify this. Let's bring the minus sign out in front. So the Qm, maximum charge, that's C epsilon naught. And tau is RC. So, yeah, the C's cancel out. And epsilon over R, let's call that I max. Yeah, maybe not I max. Let's call that I naught. Because that's what we get at t equals 0. We called I max C epsilon over tau. Actually, yeah, that's the same thing. So, yeah, and the maximum charge or the maximum potential on the capacitor is epsilon. So we charged it up. The current kept building up until the potential across the capacitor was epsilon. And so when we flip the switch, there's a potential epsilon across the capacitor, and the voltage drop across the resistor would have to be epsilon then. If we use the loop rule, yeah. So just from Ohm's law, that makes sense that I max is epsilon over R. Let's put that here as well. Okay, so let's write this here, the current as a function of time. Looks very similar. And yeah, if we plot it, it's, well, kind of going to be the same thing. We have this minus sign in front. And yeah, here the current is going counterclockwise, like the opposite direction as it was going here. So let's plot, here, we'll use red, that'll show up. So yeah, t equals 0, this exponential term is just 1. E to the 0 is 1. So we're at maximum I max, and then it goes to 0 as t goes to infinity. But again, after about 3 time constants, we're basically there. So we have this capacitor both charging and discharging. Every one of them has this factor e to the minus t over tau. And yeah, that's the capacitor. Well, that's an RC circuit. And again, right now we're hooking it up to just like a battery. So yeah, I guess that will be it for this video then. And yeah, next we'll talk about like other types of circuits we can deal with. We're dealing with direct current right now. We just have a battery that's applying the power to the circuit, and batteries just keep pumping out current in one direction. Later we'll talk about alternating current.